Hello everyone, myself Rishad Mullah.
Hello everyone, myself Git Aditya Design.
Hello everyone, my name is Surya Sinde.
Hello, everyone.
Uh, our topic name is Introduction to Adaptive Filtering. Adaptive filtering is a powerful signal processing technique that adjusts its parameters in real time to optimize performance in changing environments or dynamic systems. This introduction will explore the fundamentals of adaptive filtering and its applications. Adaptive filtering is a signal processing technique used to improve the performance of system by automatically adjusting filter parameters in response to changing the signal characteristics. Next slide. Uh, LMS stands for least mean squares algorithm. First type is adaptive filter. The LMS algorithm is used to adaptively adjust the coefficient of an adaptive filter to minimize the mean square error between the filter output and desired signal. Noise cancellation. Application of adaptive filters is a noise cancellation used in hearing aids and communications systems to minimize the background noise. Echo cancellation improves call quality in telecommunication system identification, estimate system parameters based on observation input or output data. The second type is gradient descent. Uses a gradient descent approach to iteratively update the filter coefficients in the direction of negative gradient, the mean square error. The advantages of mean gradient descent is simplicity. The LMS algorithm is easy to implement and computationally efficient. Adaptability. It can adapt the changes in the input signal statistics over time. The third type is convergence. The algorithm continues to update the coefficient until the filter output con- converges to the desired signal, providing an optimal solution. The third one is motivation for adaptive filtering. Time varying environment. Adaptive filter can adapt to changes in the statistical properties of input signal or system characteristics over time. Uncertainty and noise. Adaptive filters can effectively remove unwanted noise and interference, providing improved signal quality in uncertain environments. Third one is complex system. Adaptive filter can model com- composite compensate for the complex non-linear behaviors of dynamic systems, making them unuseful in a wide range of applications.
LMS algorithm
Aditya.
and properties. Uh, the least means squares is LMS algorithm is an adaptive algorithm primarily used in signal processing and control applications. Minimize
कर चालू.
LMS algorithms and properties. First one is simplicity. The LMS algorithm is computationally efficient and easy to implement and making it suitable for the real-time application. Convergence. The algorithm can converge to the optimal winner solution under the certain conditions, such as stationary input signals. Third one is stability. The in LMS algorithm is generally stable, but the step size of the parameters must be carefully chosen to ensure the stable. Tracking the ability, the LMS algorithm can track slowly varying systems parameters, making it suitable for adaptive applications. There are also so many applications like mean square error minimization, square stick gradient descent, and robustness. Next slide.
LMS algorithm applications. First one is signal processing. The LMS algorithm is widely used in adaptive noise cancellation, echo cancellation, and channel equalization in communication systems. Biomedical engineering, the second point. LMS based adaptive filters find application in biomedical signal processing, such as in the removal of the artifacts from electrodiagram, ECG, and electroencephalogram, EEG signals. The second is control systems. Adaptive filtering using the LMS algorithm is employed in control system to adapt to changing plant dynamics and improve the system performance. Third one is sensor networks. LMS based adaptive filtering is used in sensor networks to perform the tasks like target tracking, localization, and disturbed signal processing. Next slide. Adaptive filtering using algorithms. Versatility. The LMS algorithm has widespread application in various fields, from the signal processing to biomedical engineering and control systems. Second is tracking ability. The algorithm's capability to adapt slowly time-varying systems parameters make it suitable for dynamic environments. Third one is emerging trend. The advancement in machine learning and edge computing are opening new possibilities for the powerful and distributed adaptive filtering solution. And the fourth point is future direction. The combining the LMS based adaptive filtering with emerging technologies like IoT, Internet of Things, will enable the real time intelligent signal processing at the edge. Next slide.
Advantages and limitations of LMS. Advantages: simplicity and low computational complexity, robust performance in the presence of noisy input signal, ability to track slowly time varying system parameters, guaranteed convergence under certain conditions. Limitations: slower convergence compared to other algorithms linked RLS, sensitive to the state size parameter, may not perform well in highly non-stationary environments. Limited ability to handle colored input signal. Next, adaptive filtering using LMS algorithm application. Speech enhancement. The LMS algorithm is widely used for noise cancellation and speech enhancement in telecommunication, improving audio quality in devices like headphones and smartphones. Biomedical signal processing. Adaptive filtering with LMS is crucial for real-time monitoring and analysis of psychological signals like ECG, EMG, and EEG, enabling better diagnosis and treatment of medical conditions. Sensor network and IoT. In distributed sensor network and the Internet of Things, LMS-based adaptive filters perform tasks like target tracking, localization, and distributed signal processing at the edge. Also, noise cancellation, removing noise from AC electrical measurement, echo cancellation. Next slide. Emerging trends and adaptive filtering. Machine learning powered adaptive filter. Integrating machine learning and the neural networks with traditional LMS algorithms to enable more robust self-tuning adaptive filters. Second, distributed adaptive filtering. Leveraging edge computing and IoT devices to perform real-time decentralization adaptive signal processing closer to the data source. Third, hybrid adaptive technique, combining the strength of different adaptive filtering algorithms such as LMS and RLS to create more flexible and powerful solutions. The LMS algorithm uses a gradient descent method to update filter coefficient based on the instantaneous error signal. It is also used to minimize the expected value of squared difference among the estimate output and required response. Next.
In conclusion, we can see adaptive filtering, especially the LMS algorithm, it's still a crucial tool in a many fields. But as we look to the future, advancements in a machine learning, IoT, and edge computing are creating exciting possibilities. We are moving towards a real-time distributed and filtering the solutions that are more adaptive and capable than ever. So, in summary, adaptive filtering is evolving with the technology, setting the stage of new and improved applications across the various industries. So, next we see the code. So, next we see the code. This code demonstrates adaptive filtering using the LMS, that is a least mean square algorithm. It takes a noisy input signal and tries to filter out the noise to match a desired signal. The adaptive filter continuously updates itself to reduce the difference error between the noisy signal and the desired signal. Next, we see the code. The first instruction n is equal to 500. This defines the number of sample in the signal. MU is equal to 0.01 is the learning rate or step size which control how quickly the filter adapts. The next instruction, filter order, is equal to 10. It is used to set the number of coefficient in an adaptive filter. Next instruction we used for generate the input signal. N is equal to RANDN 1 comma n. It generates a random white noise. Next instruction, desired signal is equal to sine, and this equation it creates a desired signal as a sine wave. Noisy signal is equal to desired signal. Instruction we use for add the noise to the desired signal to create a noisy signal. Next instruction we used for initialize the LMS filter. That W is equal to zeros, filter order 1. It initializes the filter weight to 0. X is equal to zeros, filter order 1. It creates a buffer to store the recent samples of the input signal. Output is equal to zeros, 1 comma n will store the filter's output over a time. Error is equal to zeros, 1 comma n will store the difference error between the desired signal and the filter's output. So this plot shows the desired signal, which is a clean sine wave without any noisy. This is the target signal that the LMS adaptive filter is trying to match by removing a noise from the noisy input signal. So this plot displays the noisy signal, which is desired signal, plus some added random noise. It represents the input to the adaptive filter. The noise makes the sine wave less smooth and harder to interpret, simulating a real-world scenarios where signals often contain unwanted noise. Third is the error signal. This plot shows the error signal, which is the difference between the desired signal and the filter's output at each step. Initially, the error is large because the filter starts with a weight set to 0 and doesn't it match the desired signal. Over a time, as the filter adapts and learns, the error should decreases, indicating that the filter output is getting closer to the desired signal. The error signal plots helps us see how well the adaptive filter is performing. If the error approaches 0 to become relatively small, it means the filter has successfully learned to remove most of the noise and the output is close to the clean sine wave. So the code also prints the final value of filter weight. This weight reflects how the filter has adapted over a time to reduce the noise and match the desired signal. The final weight represents the learned parameter that the LMS algorithm has optimized for the given input signal. In a summary, if the filter has performed well, the error signal should decrease over time, showing that the filter is closely approximating the desired signal, and the plot allow you to visually assist the performance, and the final bit indicates the learned setting of the filter after adoption. Thank you. See the output. The code produces three main outputs which are displayed in a separate plot. Here what we see at first is a desired signal in first plot. This plot shows the desired signal, which is a clean sine wave without any noise. This is the target signal that the LMS adaptive filter is trying to match by removing the noise from the noisy input signal. Second is the noisy signal. This is the second plot. This plot displays the noisy signal, which is the desired signal plus some added random noise. It represents the input to adaptive filter. The noise makes the sine wave less smooth and harder to interpret, simulating a real world scenarios where the signals often contain unwanted noise. Error signal, third signal, that is a third plot. This plot shows the error signal, which is the difference between the desired signal and the filter's output at each step. Initially, the error is large because the filter starts with a weight set to 0 and doesn't match the desired signal. Over a time, as the filter adapts and learns, the error should decreases, indicating that the filter output is getting closer to the desired signal. The error signal plot helps us see how well the adaptive filter is performing. If the error approaches 0 or becomes relatively small, it means filter has successfully learned to remove most of the noise and the output is close to the clean sine wave. This code also prints the final value of the filter weight. This weight reflects how the filter has adapted over time to reduce the noise and match the desired signal. The final weight represents the learned parameter that LMS algorithm has optimized for the given input signal. So, if the filter has performed well, the error signal should decreases over time, showing that the filter is closely approximating the desired signal. The plot allows you to visually assess the performance and the final weight indicate the learned setting of the filter after adoption. Thank you.